Hello, everyone. My name is Iman Chalabi. I'm Product Marketing Manager at Analog Mixed Signal Division here at onsemi. And today we are going to talk about onsemi's current sense amplifier design tool. We are going to talk about purpose of this tool and go over its main capabilities and talk about how it can help system designers to pick a proper current sense amplifier for their design needs. For any current sense design, system designers typically have to look at multiple current sense amplifiers and gain options, and then factor in external contributors like shunt resistance, shunt tolerance, amplifier gain error and offset. And sometimes in addition to those, you're also dealing with optional input filter resistors and their tolerances, all of which need to come together in an iterative process to meet the system accuracy, power loss target, and cost targets. As you can imagine, this can quickly become an overwhelming process. And over the last few years, we've had a lot of customers asking us for help with accuracy calculations. And because of all of those feedbacks, we have developed our current sense design tool, which is an online tool that simplifies and it speeds up the design of shunt-based current sensing circuits. As you will shortly see in this tutorial, this tool brings all of these steps into a guided workflow. It starts by asking for system level requirements, and then within just few seconds, it recommends suitable parts from onsemi's current sense portfolio. One important thing to call out here is that this tool only focuses on DC performance. It doesn't model transient or noise behavior. It uses worst case maximum and minimum datasheet specification rather than just typical value, which is one of the key advantages of this tool because it allows designers to evaluate realistic band rate conditions. You can access this tool by going to onsemi.com. Under Design tab, you can see Current Sense Design Tool here in this section. And when you click on it, it will take you to our Design Tool page, which provides some introduction about the tool, what it does. But at the top, you can see there is a Design Now button where if you hit, it will take you to the actual tool. And when you open up this tool, you first encounter this page. In this section, in the right-hand side table format section, designers can insert their known system parameters. A lot of designers know they need to measure current in their system. They aren't sure where to start. This input table is a great starting point because it captures the key criteria for designing a shunt-based current sensing solution. As a user, you can insert your known VS supply voltage requirement here, as well as input common mode voltage requirement at the top. And then, as you can see, we have field for full scale positive and negative current range, which is basically the maximum current you want to measure in each direction, and the current that is going into your shunt resistor. In this case, default is 20 amp to -2 amp. And this tool uses these values to determine directionality. If the full scale negative current is anything other than 0, like -2 in here, that means this is a bidirectional current measurement, and our tool is going to recommend bidirectional current sense amplifiers with external VREF pin only. This is commonly used in applications where current can flow in and out of a load. Example is, for example, battery charging and discharging monitoring system, motor drives with regenerative braking, onboard chargers, DC to DC converters that support power flow in both directions. On the other hand, if your application only measures current in one direction and is what we call a unidirectional measurement, you can simply set this negative current value to 0. And as you can see in here, we currently have -2 amp for full scale negative current, which indicates a bidirectional current measurement, as we mentioned before. And we are dealing with a bidirectional current system. And the current sense amplifier will typically include a VREF pin. And this external reference voltage pin is called zero current reference voltage, and it defines basically the zero current points of your measurement, and anything below this VREF value represent current flowing in a negative direction, and anything above the VREF value represent current flowing in a positive direction. And this tool uses this reference voltage and its tolerance, as you can see we do have a field for it here, to model the worst case boundary condition, all of which you will clearly see visualized on the next page when we get there. And you're going to see how shifting this voltage reference moves the entire output range up and down. This is especially important and useful when designing systems that need to interface cleanly with an ADC, where you're trying to maximize resolution while keeping the output signal within the ADC input range. So if you're working with a bidirectional current sense amplifier and you're working on a bidirectional system, then your system usually has a defined zero current sense voltage. And this is a field where you want to enter that value there. And then next, you can see you can also insert the maximum and minimum operating range in this field, this two couple of field here, which is kind of important because temperature affects everything. Extreme temperature swing can affect amplifier offset, gain error, common mode rejection ratio, as well as external factors such as shunt resistance, which is going to change your boundary condition. And mean max operating temperature tells the tool what die or PCB temperature extreme to use for worst case DC calculation. And this is very important in application, automotive application, industrial application, and outdoor energy type of application where ambient and broad temperature can vary widely over time. Next, as you can see, we do have an input filter resistor section. If your design doesn't use an external series input resistor for filtering purposes, you can leave this section at 0 ohm. However, if you plan to use input filter resistor, you can enter resistor value and its tolerance in these two fields, which this tool is going to use these values to calculate the overall DC impact in the accuracy results. Because as you know, resistor will add additional mismatch and it will downgrade the performance. Even if your system is going to have input resistors, we usually recommend as a good first approach to just leave this field as 0 ohm and review the performance without any filter resistor. And then in the next section, you're going to see that you can easily add the intended resistor values and see how they affect your boundary condition and error curves. And you can tweak those resistor values and refine your design. You will often see these resistive filtering come into the play in applications such as motor drive and switching power supply application, where series resistors are added again for filtering purposes to help with the EMI and input filtering. And also one thing to note here that we cap this resistance value at 50 ohm here, because that is usually the maximum ohmage you would need for this type of purposes. They are typically around 10 to 15 ohm at a given design, but we have a limit of up to 50 ohm for some flexibility. Next, you can see, or possibly the most important knob in this tool, which is shunt power requirement. This is an important knob because it drives the trade-off between accuracy, power loss, and cost. One of designers' burning question when it comes to the shunt-based current sensing design is what shunt value and amplifier gain do I need to pick? And that really depends on your power requirements. If you can allow higher power loss, our tool can often recommend a higher shunt resistance within your budget to help optimize the cost. If you need low power loss, then the recommended shunt will probably be a higher cost but lower resistant technology to reduce power consumption. So in this tool, we ask about the user's maximum shunt power budget, and they can insert it in this field here, and shunt resistant tolerance and those type of information. And based on these inputs, we provide a starting points for your internal shunt resistance and amplifier gain. And again, in the next page, as you will see shortly in a design worksheet section, you can tweak the shunt value, tolerance, tempo, as well as different amplifiers with the different gain options to fine tune your final solution and see what is the best combo for the results that you're trying to get. Lastly, at the end, we do have our full load accuracy field, which sets your required percent accuracy at a high load. The tool uses it as a pass and fail target and flags design in red if you don't meet the full load accuracy goal that you set in here. But we will see this in the next page. But before we move on from this page, I would like to mention that you can save your simulation in the next page. And in this section, in this page, you can see that we have an import button that will allow you to pull up and load your previous work from previous sessions. And also, if you scroll down at the bottom of this page, we have an instruction button, which you can see all the stuff that we are covering today. Everything could be found in this instruction for later references. Now, let's keep all the values as default as they come here, and maybe change our full load accuracy to 2% for purpose of our example, and hit submit and go to the next page. Okay, after you hit the submit button, tool will take you to part recommendation page where you can see list of recommended parts from onsemi current sense amplifier portfolio based on the inputs that we inserted, with some information about each part's gain, package, and link to their data sheet, as you can see in here. This is a list of parts that could be a good fit. We don't know yet at this point, and we are going to explore in the next page in our design worksheet. For now, let's take our first pick here, NCS199, for this design iteration, and select a part and go to the design worksheet. Okay, this is the main design worksheet page we've been talking about. Everything on this page is generated based on the inputs you entered earlier, and the amplifier is selected in previous step. Let's quickly walk through this page before we start tweaking anything. As you can see on the right-hand side in the middle of page, you see our output voltage versus load current plot in here in this section. This is where you can clearly see whether your design stays within a valid boundary condition. Just below that, you also can find a couple of error plots that show how accuracy behave across the operating range. And also you can see a few different error messages here, especially at the top in the error section. You notice a few warning messages and errors, and also a few exclamation points in a design estimation section. Basically, all of these are red flags that needs to be addressed before we move forward and finalize our design. And also you can see a few errors on a error plots, a few warnings on error plots at the bottom, which are saying display data are invalid. This kind of means don't rely on these accuracy numbers just yet. And that is because at this stage, the design hasn't met the boundary condition showed at the top. So basically, we have a clipping issue with our plot at the top, and we have a voltage full scale error here, as you can see, exclamation. So all of these needs to be fixed before we get the reliable information on error plots that we can basically read off of these plots. Before now, we need to first fix the voltage full scale error. And this is basically the key takeaway here is that before interpreting any of the error plots, we first need to tweak our parameters so that the output voltage plot in here stays fully within a valid operating window. And once that is done, then the accuracy results at the bottom shown in this plots become meaningful, basically. Also, on the left-hand side of this page, you will see that you have access to all the input parameters that we talked about earlier. You can adjust any of these values right here, hit enter, and instantly see how those changes affect the boundary condition and performance on the right. Toward the bottom of this section, you will see both estimated shunt resistance and recommended shunt resistance that is currently being used in this design. And these values aren't fixed, and you can tweak them and immediately see how the result change on the right-hand side. You also see that you have access to the estimated gain with the recommended gain that we are kind of currently are using and we selected in a previous step. Just like with the shunt, you can try different amplifiers here. You can pick and choose different amplifiers with different gain options and see how those choices impact your performance, boundary condition, and any warning messages on a plot. This page is really where the iteration happens. You make the small adjustments on the left and immediately see the impact on the right, and that is going to help you to converge on a clean, compliant design in a timely manner. Now, let's dive deep into errors that we are seeing in this example and figure out how to solve them. Here, as you can see, we have two main errors. There are different explanations and warnings, but as you can see, right now we are getting error on a voltage full scale range and also a full load accuracy percentage. And that's because these are not meeting the target we set earlier. Whenever that happened, as I mentioned before, the first place that you want to start and look is the output voltage versus load current plot here. This is the tool's primary validity check for the entire setup. It shows the nominal output voltage along with the upper and lower worst case boundary voltages across the full load current range. All of these curves are built again using typical minimum and maximum datasheet specification. And the designer's job is basically is to tune parameters on the left-hand side, like a shunt resistance, amplifier gain, VREF, and all the tolerances so that the both nominal curve and worst case boundary curves stay inside the valid operating window shown in this plot. And the valid operating window are dotted red and blue lines. So as you can see in here, we do have some clipping, which is kind of unacceptable and is creating our voltage full scale error shown at the top. So we need to do this so this output is optimized and sitting between these two lines and then move forward. And so let's do that. In this case, one simple way to fix the boundary issue is to slightly reduce the shunt resistance, and that changes the slope of our output voltage curve. And let's just do that. As you can see, currently the shunt resistance set at 2.2 milliohm. And if we slightly reduce this to 2 milliohm and hit the enter, let's go back up. As you can see, the slope changed and the curve now fits nicely within the window, just above the ground and just below the 5 volts. All of them are now safely within a allowed operating range set by the system. At this point, if you go up, you notice that our voltage full scale error has disappeared. However, we are still having our full scale error, accuracy error warning, and that is because we are missing our 2% target that we set up at the initially at the like an input filter input table section, and we are currently getting 3.48%. One way to improve the full load accuracy would be to choose a higher accuracy amplifiers. Right now we are using our NCS 199, and so for example, if you go back to this section and click on it, and if you pick, let's say, for example, our NCS 2167X, which is a higher accuracy part, and select that one, you will see our final full load error is 1.9, and you can also confirm it here, 1.93, and that satisfies our 2% goal that we set. And that, for example, removes all the error from this design. And now let's look at another common design question that we get. For example, what happens if you add an input filter resistor? For this particular device, NCS 2167671, there is an internal resistive network at the input of this device. So when you add a series input resistor, say for filtering, that resistance interact with the internal resistive network and can have a more pronounced impact on overall accuracy. For example, let's go and add 10 ohm as a filter, 10 ohm input resistor to our design, and hit the enter. And you will see that the error curves are no longer symmetrical anymore. The positive error right now is 0.2, while the negative error is minus 0.4, which kind of translates to different accuracy levels, 1.42% versus minus 2.4%. And so as you can see, there is some skewing because of the effect from that resistive network that we just talked about. And this skewing becomes more noticeable on some of our devices, like, for example, 2167X family. But depending on the input architecture and whether or not if you have a input resistive network or not, you can see this is skewing in some of our devices, but not in some other ones. In this particular example, if you are going to use the system as it is, and you can tolerate this asymmetry as you're adding, like, for example, filter resistance, and it is perfectly fine with you, you can just take this and move ahead with your design. However, if this is not acceptable, we do have other options as well. For example, 21671 can also come in a Macro 10 package, where in this package you will have access to dedicated capacitor input pins in here, Cin plus and Cin negative, and as you can see these input pins in a diagram in here, which allow you to add filter capacitor across matched internal resistor directly, avoiding the need for external series input resistor altogether. And that could, for example, preserve your accuracy and symmetrical behavior that you might need. And this really, again, brings us back to the iterative process we talked about earlier. This tool makes it easy to try different amplifier, different gain options, different shunt values, and immediately see how each of these choices affect the boundary condition and accuracy. You iterate, compare, converge until you land on a solution that is basically what you're looking for.